sections. And today we have the pleasure to have Dr. Martin Skaczynski to lead us with this section. Dr. Skaczynski is a senior domain lead at Amazon Web Services. He's a data scientist, a machine learning engineer with a broad scientific background that ranges from biochemistry to epidemiology. So if you are looking for a rare multidisciplinary data scientist, then here is one that you are going to have today. Dr. Skaczynski has a PhD in tumor biology, MPH in epidemiology and biological methods from Johns Hopkins, BA in biology, MS in biotechnology. So he has so many different degrees. He is someone who never stops learning. If you go to his LinkedIn site, you will see that for yourself. So I've also noticed that he speaks English, French, Polish, Russian, and Spanish.
Yeah.
But for our purposes, we are going to stick with English. So Dr. Skaczynski is all yours.
Yeah,
and thank you for accepting this offer to help us.
Yeah, thank you so much. That was for the very kind introduction. I'm actually learning Portuguese now, and I feel like, you know, not comfortable speaking yet, but when I turn on a show or a movie in Portuguese with subtitles, you know, I feel like I can understand pretty much everything. So that's coming along. And then, yeah, I have, I was at one point addicted to collecting degrees. I think I've moved on now to collecting tech certificates. But yeah, and you can see all that on my LinkedIn. That's true. Okay, I'm gonna go ahead and share my screen. All right, so let's go ahead and try this. Okay, so what you're seeing right now is the GitHub repository. And I have in this module 3 data clustering and dimensionality reduction directory in this GitHub repository, I have the materials, right? So I'll show you the materials that I have for today. We have some slides, we have a notebook, we have a Python script, there's this R Markdown file, and then another Python script and some data. And then here, this is something that I think maybe will be a new concept for a lot of people. This is a so-called Git submodule. And what it does is it links to previous resources, okay? So if you click this, it's kind of neat, I feel. You know, it takes us back to resources, previous resources, right? And that's something that I can do when I work with Git. I work with Git in an environment called the command line, using a command line interface. So I'll show you my command line interface. It looks like this, okay? And I type in commands and I do git submodule add and then the URL, and it puts it in this kind of link that you can access in GitHub. Right, so things are kind of connected together, okay? And then Git kind of, the Git version control system manages this, right? So first thing I wanted to highlight are these resources, these materials, right? The next thing that I wanted to highlight is in the chat, so in the Zoom chat, I shared a link to some slides, okay? And what I can do is I can share that. I can actually paste that in again, because I think if you just joined, maybe you can't see previous chat messages, but there it is again. So if you click on that, it'll take you to something that looks like this, right? So these are some slides. I have to correct this. It should be module 3. It says module 4. But these are some slides kind of to get us started. But what I would want to do is spend most of the time that we have working on code, working in a Jupyter notebook, right? So I believe that thus far you've had some exposure to working with Jupyter notebooks, right? So here I can see you have from module 1, data preparation, exploration, visualization. You have several Jupyter notebooks here, right? But in terms of how to get this set up, probably the easiest way to get the latest materials, if you don't have Git, is to click this little green button, do download a zip file, okay, and then take that zip file, unzip it, and then in this directory you'll have all of the files that I just showed. If you want to try obtaining this with Git, there are other options. I'd say that maybe the second easiest way is to use GitHub Desktop. Then you won't have to be downloading zip files, unzipping them. You can use GitHub Desktop to just pull in the latest changes, not just for today, but in the future, right? And so it's going to be, I think this is, it takes a little bit more work to get it set up. But once it's set up, then it's a lot easier. You just click a button and the resources are up to date, okay? These ones up here, all three of these options, those are things that you would do in the command line. So you would type in commands. Like, so for example, I could do git pull, right? And it says, okay, it's already up to date. I have the latest materials up to date on my computer, okay? So once you have that, hopefully you already have those materials one way or another on your computer. The other thing that we're going to need is we're going to need a Python environment. And the Python environment that I always recommend everyone to start with is Anaconda, right? If you were working with pandas earlier, you probably have Anaconda installed. If you don't have Anaconda, it's a simple download. You can use the graphical installer that's provided, and it will install it on your system. There's maybe one more thing that I want to say. When I say graphical installer, I'm making a contrast between what is a command line installer and one that has a graphical user interface, something you can click on. If you're clicking, you're using a graphical user interface. If you're typing commands into a command line, that's a CLI or a command line interface, okay? So I already have Jupyter running because I had this kind of set up ahead of time, okay? So my Jupyter is here, and I have all these resources, okay? So I'm going to open up the notebook. We have here, this is cluster, IPyNB, okay? And again, I need to fix that. It's module 3, not 4. But here's the intro, right? So I want to put this kind of in context of where what you've done already, right? So I see here that there's data preparation, exploration, visualization. So I'm expecting you to have already done that. Module 2 was classification models. That's what I see here in GitHub. So you already have some exposure to classification. So I'm going to ask you questions, okay? I'm going to ask you questions, and I'm going to wait for answers, okay? So here's the first question, okay? Can someone provide a description of what is machine learning? And I have some, a list here, right, of a process. But if you could maybe provide a definition in your own words, okay? All right. And if I don't hear from someone, I'm going to call on someone, and I hope that's okay. If you don't have to turn on your camera, but I'll want to hear from someone, right? So also writing in the chat is fine. If you want to interact with me that way, that's also perfect. Okay. Let's see. So I'm gonna just try someone. Okay. Okay. So I'm gonna call on someone, and I hope this is okay. Maybe you weren't expecting to have to interact with me, but you will have to interact with me. Or at least I hope you will. Okay, I'm going to call on someone. Temilola.
Hello.
Hi, hello, good morning.
Good morning.
Hi. So the question is, what is machine learning in your own words? And if you're not too sure, that's absolutely fine.
Sure. I mean, I think of machine learning as an entire process.
Yep.
Basically, finding data, cleaning data, analyzing data, and then using the, I guess, technical machine learning process to just gather outputs.
Great.
Do the analysis to make better solutions.
Great.
Yeah.
Great. Okay, so I'm going to highlight some of the things that you said. Okay, so I liked how you said outputs, right? So if you've got outputs, you probably also have inputs, right? So these are going to be, you're going to be using algorithms or models, right? And those models are going to take inputs and give you outputs, right? And then there's something that's happening in between the inputs and the outputs, right? And what that is that there's this algorithm that's learning from the data. It's learning what it's supposed to do based off of the data. So there's the learning portion, but you definitely have the outputs, and the outputs allow you to do something, right? Whatever the task is, it allows you to hopefully, like complete that task, solve the problem, answer the question, but it involves an algorithm learning from the data. The data are the inputs for the algorithm. That's a great definition, okay? All right, thank you so much, Temilola. That was perfect. I'm going to call on someone else now. The questions are getting harder, so if you haven't, you should. It's in your best interest to volunteer, right? Oh, I see Jennifer shared something. Okay, so Jennifer says, process of using algorithms to train computers to learn from data. Excellent, right? So that training is really an algorithm learning from the data. Okay, so something that's interesting about machine learning is it's not, let's say, necessarily a pure function in the mathematical sense, in that it just takes an input and provides an output without being changed, right? So we would say that maybe that the function is idempotent in the sense that it can be always reused. It never runs out of batteries. It will always be able to accept new data, process it the same way, and then return consistent results, right? Without being changed in the process, right? But when we're doing machine learning, we train a model, it learns from the data, and it adapts its process to that specific data and gives us back a result that's tailored to the data that was provided, right? So the algorithm is learning from the data, it's being changed, it's adapting to the data, right? And that's something that's cool and unique, okay? All right, so next question is, what's the difference between supervised learning and unsupervised learning?
Supervised learning has labels and unsupervised learning doesn't have labels.
Perfect. Anthony, that was excellent definition there, right? And so let's maybe elaborate a little bit on what do we mean by labels, right? So labels are going to be, so you have labeled data, you have some kind of label, right? That label we can call an answer, right? Instead of calling it a label, we could call it a target or a response. In statistics, you would call that a dependent variable, right? So in supervised learning, we have a dependent variable. In unsupervised learning, we don't. Just that concept doesn't exist, okay? And so can someone say what's an example of either one, unsupervised, supervised, some example of either one at least?
Hi, this is Sovita. I'm going to give it a try.
Sure. Yeah.
What about electronic health record data? With that, I think that's a little bit of both, right? Or
okay.
More unsupervised?
So real world health data is really electronic health records. I call that real world evidence kind of data. That's real world. We would have to do something with that data, right? What we could do is we could try to predict let's say we've got different classes of patients based off of their electronic health records. We could try to predict, basically put them in a certain category, okay? So what could these categories be, all right? These categories could be, let's say we're an insurance company and we're only looking at the bottom line and we only care about dollars and cents. And we would categorize our patients, are basically people who are paying us money, our customers, as either people who are risky or not risky, okay, based off of their electronic health records, which we have access to, okay? So then we've got those two categories. We've got risky, not risky. If someone's risky, then we increase their premiums, okay? Because we want to, we want to get more money from them for sure, right? But if someone's not risky, we keep the prices as they are, right? And that would be an example of classification, right? So kind of elaborating or kind of extending what you said, that would be classification would fall here under unsupervised learning, okay? Why? Because we have these labels. We have a concept of labels. We have risky and not risky, okay? I worked for a long time at National Institutes of Health in cancer. And so for me, at that point, the most important labels were either benign, malignant, right? Cancer diagnosis, no cancer diagnosis, mortality from cancer or not, right? So it's usually kind of some kind of binary classification, yes or no, right? Alive, dead, healthy, diseased, this type of thing, right? That's classification and falls under supervised learning. All right. Okay. So the reason why I'm focusing on classification is I'm expecting you to already have done that at this point in module 2. All right. Thank you so much. And is it Jovita or Jovita?
It's Spanish, right? So it's Jovita in Spanish, but Jovita in English.
Jovita in English. Okay. Which do you prefer?
Either or.
If I say Jovita, is that okay?
Yeah, you actually say it like how we say it in Spanish. So yeah.
Yeah. Good. I'm glad. Okay, so this is great. Now let's turn from supervised learning to unsupervised learning. So Anthony gave us a great definition. In supervised learning, we have these labels. Okay. So again, our labels and classification could be any of these binary categories that I talked about. You can also have multiple categories, right? So for classification could be, today it's sunny in the DC area, which I'm very glad for, but typically it's been very, very rainy and there was no sun for, I think, like at least a week and a half here in this area. In part, it was at least partially Ian, at the point when it got here, it was I think a tropical storm. So Ian was partially to blame, but now the sun is shining, right? But we could come up with a prediction algorithm that will predict whether it's going to rain, yes or no, and it'll have certain inputs. So it will have meteorologic data, data about the weather, and then we're going to predict, is it going to rain tomorrow? Yes or no. And that's binary classification. Will it rain or will it not rain? And that's it, okay? Then we can say we're going to have multiple classes in our classification. How much is it going to rain? Is it going to rain a lot, a medium amount, a little, or not at all, right? And we've got however many classes, right? And that's still supervised. We have those labels. That's what we're trying to predict. We're trying to predict, these categories, right? There's another type of supervised learning, which is similar to classification, called regression. Regression would be how many inches of rain are we going to get tomorrow, right? Because it's not categories. We're not predicting discrete categories. We're predicting a range of values. We could get 1/2 inch. We could get, 3.7 inches of rain tomorrow. It's a continuous value. So classification is discrete categories, and regression, you're predicting continuous values. So there it just depends on what type of label do you have. Is it discrete or is it continuous? Okay, discrete classification, continuous regression. Okay. Now let's shift over to unsupervised learning. Now unsupervised learning, at least in this course, is kind of uncharted territory, I think. All right. We don't have labels. So how does that work? We're maybe not even doing prediction, and then maybe we don't even have really a training data set. We just have a data set, right? We're training the model on the data set, but we're not doing something that's super common for supervised learning, which is to do data splitting. We don't have to do data splitting in unsupervised learning, okay? So for supervised learning, we would do a train test split. We would have a training set and then a test set, okay? In unsupervised learning, we don't really have that. Okay, we just drop in our data and see what happens. Yeah. Okay. Supervised learning, right? As Anthony said, we have data that's labeled. Okay. We've got labeled data, and then we have our predictors, which is usually a matrix, and then we have a vector of labels that goes along with this matrix of predictors. Okay. And then classification, we're going to have these categories are the labels. And then in regression, we've got continuous labels. Okay. All right. And then in the classification materials, I would assume you went over something like logistic regression. It's a common classification algorithm. Okay. All right, but now we're going into unsupervised learning. So we have unlabeled data that simply doesn't have any labels. That concept just doesn't apply. All right. So what do we have? What kind of algorithms do we have here? I mentioned logistic regression is for classification, but here in unsupervised learning, we've got clustering. Okay. As one of the main examples of unsupervised learning. Okay. There are other ones. Here are some fancy ones, but that's a little bit out of scope for today. We're going to have dimensionality reduction as another one, right? So what else would I put here? I would put, you can also have anomaly detection under unsupervised learning, but we're going to focus on clustering and then later on dimensionality reduction, okay? Yep, and so Krishna, you're exactly right. In unsupervised learning, the training data consists of variables without any corresponding target values. Yep, exactly. And there's so many names for all of these different things. The labels, you can call that target values, you can call those response values, you can call that your dependent variable values, right? Absolutely, absolutely, that's exactly, okay? So this is a flowchart from Scikit-Learn, and I'm in my browser, so I can kind of nicely zoom in on different parts here, right? So first of all, what's Scikit-Learn? I would expect you to already be familiar with Scikit-Learn since you did classification in the module preceding this one. So Scikit-Learn is the flagship Python library for machine learning. When I say flagship, I say it's like the main one, right? Essentially, if you're doing machine learning in Python, you're probably using Scikit-Learn. If you were trained to do machine learning in Python, you definitely have experience with Scikit-Learn. Some people maybe kind of skip Scikit-Learn and go on to, for example, if someone only works with neural networks, it's possible that they haven't used Scikit-Learn. But I kind of expect everyone who does machine learning to at least, have some experience with this, right? So this is the main library in Python for doing machine learning, okay? And this is also called cheat sheet, but really what it is it's a flow chart, right? Kind of a decision chart that we can say, and then which algorithm are we going to use? All right, and you see here, up here, there's classification, and then there's regression. All right, so I think this is a nice chart for us to look at and think about, well, what are these things, what are these decisions, right? So here it says, if we have greater than 50 samples, great, move on. But if you don't have more than 50 samples, then it says get more data, okay? And actually, I would push back on that. there are some algorithms that you can absolutely fit to less than 50 samples. And one of those would be, for example, logistic regression. If we're doing classification, I would say, sure, fit logistic regression to those 50 samples, right? Sure, more data would probably be great. But let's go ahead and fit a very simple model to the small data set, and we'll see what we might be able to learn. Okay. Okay, so logistic regression for classification, some kind of linear regression for regression, right? And I know it's confusing that this classification regression distinction that comes from machine learning, whereas the split between those names for logistic regression and linear regression that comes from statistics, kind of predating machine learning, right? And so logistic regression is a classification technique. It's a little bit hard to maybe remember at first. Yeah. Okay. Or it seems counterintuitive. Okay. So this is the first thing. After, when we have enough data, what do we want to do? We want to say, are we predicting a category? If we're predicting a category, yeah, then we say here, yes. We say, do you have labeled data? If we have labeled data, we're going over here to classification land, right? So we're predicting a category, we have labeled data, we're doing classification. Okay. And that's all I want to focus on. I don't want to focus on these very specific models here. I just want to talk about these big blobs. Okay. So if we don't have labeled data and we're predicting a category, we're going into clustering. Okay. Good. So that gives us, I think, a very clear understanding of how do we decide what type of model, right? Predicting a category, don't have labeled data, clustering. Predicting a category and we do have labeled data, classification. Okay. All right. And so unsupervised learning is down here. Supervised learning is up here. Okay. If we're not predicting a category, we're predicting a quantity, then that's regression. Okay. And then here, this is really funny, I think. Predicting a category, nope. Predicting a quantity, nope. We're just looking, right? If we're just looking, which is very funny, then we go into dimensionality reduction. Okay. And so we'll talk about dimensionality reduction, but we'll focus first on clustering. All right. And I hope you understand now this distinction. Okay. So up here, supervised learning, the distinction is predicting a category or predicting a quantity. Okay. Down here is unsupervised learning. And then where you don't have labeled data, and then it's predicting a quantity, so predicting a category down here, but we don't have labeled data, or you're exploring the data. You want to take many columns and kind of summarize them into a smaller set of columns, okay, in your data set, okay? And then your columns in your data set are usually your predictors in unsupervised learning, sorry, in supervised learning, but in unsupervised learning, your columns, you just call those features, right? So features in your data, you can also say attributes in your data set. Those are the columns, okay? Your rows here in this chart, those are called samples. You can call those examples. You can call those observations. You can call those instances. You can call those data points. There are lots of different names for rows in your data set, okay? Okay. And I think that's everything that I wanted to highlight here. Okay. So this is, I think, a very useful plot. Okay. All right. Okay, so now we're going to get into clustering. All right, and we're going to get into we're going to have some time for an activity, and we're going to also take a little bit of a break. Okay, because I just threw a lot at you. I think a lot of it was hopefully review from classification, but some of it was absolutely new. I think everything in unsupervised learning was new, right? At least in the context of this course. Okay, so we've got clustering, and I mentioned how dimensionality reduction. You're taking columns and you're kind of reducing those dimensions, reducing the dimensionality of the data set. You have fewer dimensions, fewer columns, right? So it's almost like as if you're summarizing the original data set in using a smaller number of columns. Okay, so that's dimensionality reduction. And clustering is similar, except you were working with rows, right? So we're going to have rows in the data set. Our rows can be, for example, participants in a study. Could be a clinical study, epidemiologic study, could be a marketing study, right? Could be, you know, maybe any kind of, let's say, thing that would produce a data point, okay? And so those types of examples, let's maybe talk about an example inside of this, inside of here, right? So I have here Titanic CSV, right? We'll look at this, we'll look at this data set here, Titanic CSV. I'm just looking at it in GitHub, okay? We have passenger ID. So it's clear right from the beginning. What are the rows? The rows are the passengers, okay? And then here we've got survived, 0, 1. So we could do a survival classification algorithm, 0, 1, where we're predicting survival. Okay, did they survive or did they not survive, right? Okay, and here in this example, our rows are passengers, okay? And then we can group the passengers into different groups, right? Those groups that we could put these passengers into would be our clusters, right? If we drop the labels here, we drop this survived column and just take our data, put it into a clustering algorithm, we would get out you know, a cluster assignment for each passenger. Okay. Okay. And then how would I process this data? I would have, well, essentially, so one of the things we could do is we could use clustering and see if we can recreate this passenger class. So here what I see is that there are 3 classes. And we could see how well a clustering algorithm could recreate this, right? Let's say we didn't have this passenger class. We could say, could clustering use the data that's available to, let's say, approximate the passenger class, right? So probably class 1 first class is going to be the, you know, first class, right? It's the most expensive. And then we might be able to say we can predict survival just using this passenger class. Okay. All right. Okay, so that's an intro to clustering. Now what I want to do is move on to an activity. And I have some links here. And first what I'm going to do is I'm going to click on this first link that's k-means. All right. And we're going to have, I'm going to show you how to use these things. And we're going to have an activity. You're going to have some time to play around with it. And then when we come back, I want to ask you these questions, right? How does each algorithm work? What steps does it take in its process? And then did you notice any limitations? Okay, and I'm missing a question mark. So let me show you how to use this tool. We'll take a break. Oh no, I clicked on it. I should have, let me go back. I'm going to command click on it. Command click on both of them. So command click opens it up in the new browser. Okay, I'm on a Mac. I don't know how it would work on Windows. I would assume control click. I don't know. Okay, so here we've got k-means. So this is our first algorithm. Okay. And then we'll go ahead and click randomly. And then we're going to pick a data set. Okay. So Gaussian mixture is going to be a data set that works, that k-means clustering works really well for. So click on that. And I look at it and I say, okay, this is something that k-means is going to have no problems. Okay. And we'll go ahead and add a centroid. So this is going to be a center for a cluster. A centroid is the center for a cluster. Okay. We've added one centroid. Right now, we only have one cluster center, so we have one cluster, and all of the observations are in the same cluster. Not very useful, not very informative, right? Doesn't help us to distinguish between these observations, between these data points. So we want to add at least one more cluster. Okay. Now we have two clusters, and you see how there's kind of a linear split. There's the cluster at the top and the two clusters at the bottom. That's great. But looking at these data, I can tell that we would want one more cluster. Okay. Now, once we have, for k-means, we have to say how many clusters we want at the beginning. So the number of centroids is the number of clusters. Okay. That's the k in k-means. Then we hit go. Okay. And we're going to hit update centroid. So they're going to move. Right, and we'll see how things go. But essentially, we already have our answer, and the answer actually is perfect. Okay, but I want to see update centroids. You see how they move? They move to the center of the cluster, and then we reassign the points. But already we're done. So this is something that's no problem for k-means. Basically, it solves the problem right away. Doesn't have to spend much time learning to get this figured out. So we've got three clusters. We've got a red cluster, blue cluster, and green cluster, and that's it. Okay, let's restart, pick centroids randomly, and then pick something that's a little bit harder. Okay, so let's do packed circles. Okay, so you can see this is tougher. All right, how many centroids do I want? Yeah, so I know from this data set that I want 7. Okay, so I'm gonna add 7 centroids, and their placement is random, and that's actually good. For our example, because we want to see the algorithm working, we want to see it adjusted. Okay, so I put those in, I hit go, and what it's going to do is it starts off with some initial clusters. These initial clusters are certainly, like suboptimal. We need to give the algorithm some time to learn, and it learns iteratively, it takes steps. Okay, so we update the centroids, and then we reassign the points. Okay, so we move the cluster centers, and then we say, okay, the points are going to be assigned to their cluster center, right? To the closest cluster center. That's where they're going to be assigned. Okay. All right, then we move the cluster centers again, and we again reassign the points. Update the centroids, reassign the points, update the centroids, reassign the points. And you see how it's going back and forth, okay, between those two steps. At some point, we're going to get to the point where continuing with these steps doesn't change anything. The algorithm has converged. What that means is that it's found an answer. It may not be the best answer possible, but it's found an answer. And when it makes small changes, it's saying, okay, this is not making any difference. I've probably converged. I'm probably done. Okay. All right. So I've got my my answer here. All right. And you can see this honeycomb structure. Right. So my algorithm here, my k-means algorithm, has helped me to describe the data using this, using these cluster assignments that are going to represent this honeycomb structure of the data. Okay. So I have 7 clusters, right? And for this, k-means actually does quite well, okay? Why does k-means do well? Even though that this is, this is a fairly tough challenge, you see, this is a lot harder than that first example that I showed, is because the clusters are all roughly the same size. They're all round, right? So I mean, round, the distribution is multivariate normal or multivariate Gaussian. Here in this case, bivariate Gaussian means that it's normal in 2 dimensions, okay? And the clusters are fairly diffuse, but they're relatively, they're distinct enough that this algorithm works well, okay? So that's how you use k-means clustering. All right, let's restart randomly, and then you can pick, we're going to also want to pick a data set that k-means doesn't work well on. And I'll give you a little bit of a hint, saying that the smiley face is k-means is not going to work well on, as well as this this other smiley face. dbScan rings, k-means, that one's more for kind of exploring this other algorithm, dbScan. Right, density bars, k-means may struggle with this one a little bit, but let's go ahead and move to this other link, right? So this other one, dbScan, okay? All right, so here it's saying for this, we don't have to pick how many clusters, right? We just let the algorithm go, all right? Let's look at dbScan in this Gaussian mixture, okay? Let's keep the default and just hit go, all right? So you see the algorithm working. It's basically building a cluster by seeing what's nearby, okay? It looks in the vicinity, kind of looks for neighbors, okay? All right, now I want to pause it here, okay, and show you how it's finished this red cluster and this blue cluster, but then not all of the points were included there. Okay, so that's something unique. K-means definitely assigns everything to clusters. And that may be the behavior we want. Maybe we do want to say, okay, these kind of outliers, we don't want those assigned to the cluster. Okay, maybe, right? But if I continue, we'll see that at some point, what it's going to do is it's going to say, okay, these ones here are outliers. Okay, and I'm not going to include them in a cluster. That behavior may be what we want. It may not be what we want. Okay, but something that I can do is increase this epsilon. So I can, because these clusters are pretty distinct, I can increase epsilon really just, all the way. And I think it's going to be fine. And I'm going to click go. And now you can see the radius that this algorithm is looking in, it's much larger. Okay. So it's not going to really, I think it's not going to leave out any points. Okay. It will cluster everything nicely, and then we get the same result as with k-means. But you see, there was some tuning we had to do. We had to say, hey, look in a larger radius than you were looking before. Okay. Let's do packed circles. Okay. So again, I'm going to do this in the defaults. And we saw how k-means, we were able to get k-means to look pretty good on this. And then you'll notice here how dbScan is not doing great, okay, here in this data set. Okay, what's going on? We're pretty much having everything show up in the same cluster. So here, dbScan is completely failing. What could I do? I could lower this range but if I lower it too much, it's not going to be able to work at all, right? So this is a data set that's actually really tough for dbScan. smiley face one. This would be super tough for k-means, but dbScan is great on this. Okay, so you see what's happening. We've got the smiley face, right? This smile becomes one cluster. That's our red cluster. And then the actual, let's say maybe the circle of the face is going to be another cluster. And then we're going to have separate clusters for the eyes. K-means would absolutely fail. For k-means, the best you could probably do is you would have one centroid here for the smile, another centroid here, and another one for each of the eyes, right? But then for the surrounding cluster, you'd have to come up with some kind of strategy. You know, there's no way you could have all of this be in one cluster, right? You'd have to split it up into clusters somehow and then combine them later, right? So here dbScan did this in my opinion, perfectly. Okay. So the performance here was optimal, absolutely optimal, right? Which is great. And then we have, some examples now of where these algorithms will perform well and other examples where they don't perform. Okay. So let's go ahead and take a 10-minute break. We'll take a 10-minute break until noon East Coast time. And what I want you to do, of course, take a break, but also if you like, play around with this and see how it performs on these different data sets. Yeah. And try to come up with some answers for these questions when we come back. All right. So let's go ahead and I'm going to do a 10-minute timer. Okay. Where's my 10-minute timer? Here it is. Okay. All right. So this is a 10-minute break until around noon. And when we come back, we'll discuss what I have there in the slides. This one. So these are the slides. Okay. Good. And then the actual questions, those are on slide 5. So actually, let me share that. The link to the actual slide. This is the slide one, slide number 5. Good. I think we're all set. Good. So go ahead, enjoy the break, play around with these on these two sites, visualizing k-means and visualizing dbScan. I'll see you after the break. Okay, welcome back from the break. All right, so hopefully you had a little bit of time to play around with these sites. Good. And I'm going to ask you some questions. Okay, so here, this is again looking for your participation. I'm going to call on someone unless someone volunteers, right? So first, what I would like to hear is if someone could explain how the algorithm works based off of your observations, right? What steps does it take in the process for either one of the algorithms, right? Oh, hold on. Let's see. So was it? So Krishna, you were not able to do this. So these links were not working for you? I would expect it to be accessible in the sense that, you could just in your browser, click and it should work, right? So, but maybe you could also just say, based off of what I showed, how these algorithms work. Okay. All right. So I'm going to call on someone. Ademola. And it can be either algorithm.
Yeah, hi. I think the k-means uses, excuse me, I think it takes like the mean of a cluster, I think, and then looks for, it like tries to include points based on how close they are to the mean, I think, and it just keeps adjusting.
Good. Wow, that's really, really good. So the observation that you just shared with us is, super, super good, because it actually includes something that, I certainly didn't mention. So let's go back and look at this Gaussian mixture, and we'll add 3 centroids and we'll have it converge, okay? All right, so the cluster centers, those are called the centroids. Essentially, they are kind of the mean, right? They're the central value of this population, right? So if we were not looking in one dimension, so if we were not looking in 2 dimensions as we are now, and we were looking in just 1 dimension, so let's try to draw it out. So here we've got nothing, and then we're going to have some data, and then we're going to have nothing again. Okay, so my drawing skills, something happened there with my drawing skills. I had a pretty good straight line, but then it fell all apart, right? And so certainly here, this point, right, would be the center, would be the mean, right, of this. Yeah, so the central point, right, the weight, the center of gravity of this distribution. And that's true, since this is really kind of normal in all directions. It's true also, in, let's say, the x-axis and the y-axis. It's true, right? So it's the center, it's the mean, yeah? And so it assigns points based off of that center of the cluster, that average value for the cluster, okay? So proximity to that cluster center, that's how it works, okay? I think that was really good. I'm really glad that you used specifically that word, okay? So the link is not working. I'm surprised by that, because it's working for me. If I paste it into the chat, this is k-means. Could you maybe try clicking on those links? Okay. All right. I think there's nothing we're going to be able to do to troubleshoot it. It's just, does a link work for you in the browser? I would maybe try a different browser if it doesn't. Okay. All right. So that was great. So that was k-means. And I think, Ademola, your explanation was excellent. Okay. Setting the bar high, it's a tough act to follow, but I'm going to want to ask someone to summarize DB-scan. Okay. So DB-scan, density-based special clustering with applications of noise is what it stands for. Okay. All right. So let's see. I'm going to call on Edmund. And you don't have to provide a textbook definition, but just something that you observed. How does DB-scan work? Okay, Edmund is still muted, so I'll move on. I'm going to call on someone else. Edmund, you can also answer in the chat if you prefer not to, if your mic isn't working, right? All right, so the next person I'm going to call on is Nanhu. Could you give us in your own words a description of how DB-scan works? Okay, so the saying goes, third time's a charm. Well, I'll keep going. All right, so Ronald, could you unmute and then in your own words, just describe what DB-scan is doing, what the algorithm is doing. Okay, all right, so I'm 0 for 3 so far. I'm gonna keep going.
I can try to take a stab at it if that's helpful.
Yes, it would be excellent, and thank you so much. You've already contributed, so that's very kind of you to volunteer.
Yeah, I don't know if it'll be correct, but I'll try.
Right.
I also read the summary a little bit, but it seems like you just start from a data point.
Yep.
And then the distance between that data point and the next data point will create an average. And then maybe between that data point and the next data point, it'll take the average of those two, and then it's so on and so forth. And then I guess the distances that are outside the current average are seen as outliers, or it continues to just build that the average, perhaps. Yeah, that's my idea.
So what I would say is I would change maybe one word in what you said. I think what you said is great. So what it is it's building a cluster, right? And it's looking in that vicinity. It starts exactly as you said. It starts with the data point, a single data point, right? And then it looks in the vicinity to build the cluster, okay? And it has to follow rules. The two rules it has to follow is now I'm providing a lot more information, right? So the first rule is, how far can it look for another data point to add to the cluster, okay? And that's going to be this epsilon. That's the radius. That's the distance it can look. How far can it look, right? Then min points. That's how many points do we need in order for it to be called a cluster, okay? If we here, how it's said is if we see 3 points and say, okay, these points are close enough together, but it's only 3 points. Can we call that a cluster? No. You know what's going to happen with those 3 points is those are going to be called outliers. If they don't have any points around them, right, using each of those 3 points as the, let's say, point of reference, if within the radius of epsilon 1, of any of those points, we don't have any other points, we only have 3 points, it's not enough points for a cluster, those are labeled as outliers. Okay. All right, so that's great. Okay, so Ademola, Temilola, thank you so much. Your explanations of how these algorithms work are great. Okay, now what about limitations? Okay, so we're almost done with this participation portion, but let's talk about limitations. All right, and I've talked about the limitations a little bit. Okay. Oh, actually, let's go back because I see in the chat. You know, what does epsilon represent? That question came a minute ago, but I'll just say again. So epsilon is the radius. Okay, and then the easiest, maybe the best place to do this exploration with epsilon is right here in these dbScan rings is what this data set is called. Okay, and you can already see how it's going to work, right? So we have min points 4, right? So here 1, 2, 3 points, not enough for a cluster, right? So these first 3 columns not good, because first column has 1 point, second column has 2 points, 3 columns. So third column has 3 points, not enough for a cluster. Okay, no clusters there. Okay, all of these are outliers. All right. Now, what about the rows? The rows are basically the distance. Okay, and we have an epsilon of 1. All right, so epsilon of 1, when they're tightly packed, it's enough. You know, that distance that we're going to be looking in, it's enough to grab these points. All right, same here, same thing here. Right here, we've got them. They're a little bit more diffuse. They're more sparse. They're more spread out, right? But still, it's enough. Here in the third row, we can still catch them, but then we're kind of reaching our limit, right? Here in the fourth row, we've surpassed our limit. We have 4 points. We have 5 points. We have 6 points, enough for a cluster, but they're too far spread out that we can't call it a cluster. It's too diffuse. Right? And so that's that epsilon. What can we do? Well, we can increase epsilon. This left slider, we increase epsilon. I just changed it a little bit. And you see already here, this fourth row, we're able to call these clusters because I increased the epsilon, right? Okay. If I continue to increase epsilon, what's going to happen? Well, this last row, these 3 on the right here in the last row, bottom row, will eventually, see how the epsilon is increasing, and then we hit that point where we can call those clusters. Why? Because without it, they're too far apart. We don't have enough points there to call it a cluster. So when I increase this to be 1.3, let's say, right? Then all of these now can be clusters, okay? What I'm going to do now is I'm going to decrease min points. And when I decrease min points, you'll see I'll be able to have this third column, have those be called clusters as well. So you see I've got min points 3. And now let's decrease epsilon. So decrease epsilon around, 1 1/4 is where it gets too small to have this last row be considered clusters. Decrease it further, right? Around 1, past 1 is where this fourth row stops being considered clusters. Okay, so it's this radius. That's how far we can move. Okay, that's what epsilon represents. Yep. Excellent. Good. All right, let's talk about limitations. Okay, so some obvious limitations, right? So k-means you have to specify how many clusters before it does any work. And you might say, how do I know? You try different values and see what works, right? Yeah, that's true. So you could run dbScan and see how many clusters dbScan does. You plot the data, you see whether it works. Okay. Also, the clusters for k-means, it works best if they don't have weird shapes. So our smiley that we saw before definitely has a weird shape, right? You know, it's got a cluster, if we want to call this a cluster, right? That is surrounding all the other data points, right? So there's another example where you've got concentric circles. So circles that have the same center, and those are different clusters. K-means won't do well on that at all. You know, you'll put everything in the center, and it won't be able to distinguish between those clusters at all, right? Here in this example, dbScan is having a little bit of trouble. What we would want to do is increase epsilon a little bit, right? So that this outer ring, so we can be sure that this outer ring has is all one cluster, okay? With this other smiley face, something that's interesting is that there are a lot of outliers, okay? And we may actually want to not have those be included in the cluster for those to be labeled as outliers. And so dbScan, that may be something we want, but that could be a limitation of dbScan. If we don't want to have things be labeled as outliers, then dbScan may not be what we want, okay? So with k-means, we have to say how many clusters we want, but other than that, we're pretty much set with k-means. We just say how many clusters we want, we get that many clusters, and every observation is assigned to a cluster, okay? So pretty clean cut. Whereas with dbScan, we don't have to say how many clusters we want, but it's gonna be good for us to think about epsilon, think about min points, right? And we'll have to discuss probably what's right for the data set, do visualization. So it's not, you know, just an off-the-shelf solution either, right? There's always some work you'll have to do, right? So Noah asks, is it fair to say that a high for this, you know, number of points for a cluster and low epsilon give power to the data? So, you know, typically like power is, you're talking about statistical power, which is going to be the ability to detect a difference that's actually there, okay? So here, I don't know, right? But in terms of, I would say it depends on the data, right? So let's think about this specific one. So high min points and low epsilon, it may not be exactly what we want, you know. So here, even though I have high min points, you know, it's not really working the way that I would want, you know. I would say here I would want to increase the epsilon and maybe have min points be a little bit lower, right? I would say it really depends on the data set, and you'll have to tune this. You'll have to tailor it to the data set, right? Okay. And then k-means, are k-means results repeatable? So for all of these, there's some randomness involved. You can make the results repeatable. What's the random thing in k-means? Well, the cluster centers, the centroids, can be assigned randomly at first. You could also not assign them randomly, and then it will be repeatable. But the way that you can do it is assign it randomly, but then choose a random seed for your random generator, random number generator in the algorithm, and then it'll always start the same one. Okay. And I can show you how to do that, right? So maybe actually let's look at it now. So we've got Scikit-Learn. Oh my goodness, my spelling. Scikit-Learn k-means. Okay. So we do k-means. And here, how does it choose where those clusters are at the beginning? Okay. So k-means plus, it selects initial clusters using a sampling method based on empirical probability distribution. of the points contribution to overall inertia. Wow, so much information there. It would just be much easier to just say, okay, do it randomly. All right. But either way, however we do it, yeah, there's this argument here called random state. So if we set random state to be some integer, the results should be repeatable, should be reproducible, so that when we rerun this data set, we rerun the same algorithm on the same data set, we get the same result, provided the same random state. Okay. All right, let me share this. Okay. For dbScan, dbScan should be repeatable. Let's look for dbScan here. dbScan, cluster dbScan. Okay. So dbScan doesn't have random state here. Yeah. Okay. So the way that we saw dbScan working is it picked a random point and worked from there. And that was really for our benefit, okay? We wanted to see how it works, and that's a logical way, because our minds are really, we do one task where we can kind of work linearly on one task. Maybe we can do it multi-threaded where we switch between tasks, but really we're just working on one task at a time. Whereas dbScan doesn't have to work that way, okay? So it can essentially work on all the points, all, you know, at the same time. And there's going to be like one result that it produces, right? So either, you know, based off of this radius epsilon in the min samples, either, you know, a sample is included in a specific cluster or it's not, it's an outlier. And there's this one answer, and there's no randomness really that we have to deal with. Same data, same settings for the algorithm, same result. Okay, so there's no random state here. Okay, no random state argument that we would pass an integer to make our results reproducible. Okay, good. All right, good. So we've covered a lot so far. We haven't done any coding. We need to get into some coding here, right? Before we do that, there's this concept of distance, right? We've got different distance metrics, and we absolutely have to talk about this, okay? Because here, metric, Euclidean, all right? So metric is Euclidean distance, all right? It's going to be one of these things that's allowed here from pairwise distances, and there's so many distance metrics, right? So city block, cosine, Euclidean, L1, L2, Manhattan. And unfortunately, a lot of these repeat, okay? So city block is the same as Manhattan, which is the same as L1. And Euclidean is the same as L2. Okay? Cosine is something separate. Okay? And then you see here, this is Bray Curtis, Canberra, Chebyshev, correlation, Dice, Hamming, Jacquard, Kulsinski, Mahalanobis, Minkowski. So many distance metrics, right? What are the ones that you should know? At some point, you may want to learn cosine. It's interesting, especially for working with text data. It's useful if you're doing natural language processing, working with text data. You may want to learn cosine. But the two you have to know for sure are Manhattan distance and Euclidean distance. Okay. And this is a great example of, and I have the reference here, of Manhattan distance and Euclidean distance. Okay. So we've got our point A, point B. What's the distance between them? Okay. Well, Euclidean distance, you would be able to just go straight through the buildings. You may describe this as it's a distance as the crow flies. It's just, you know, from point A to point B, the shortest path, right? With no obstacles in the way. Okay. But in real life, we wouldn't be able to travel like that. There are buildings in the way. Yeah. What would we have to do in real life? We would have to walk along the streets, right? I mean, maybe we could cut through a building, but still it's the same kind of idea. The critical thing in Manhattan distance is we're not allowed to go diagonal. Okay, we have to move in perpendicular directions. Okay, and so the way that I like to describe it is, if I was going to say, what's the distance between the tip of my pointing finger and the tip of my thumb? All right, so I'm gonna with Manhattan distance, what I'm gonna do is I'm gonna go along my pointing finger and then up my thumb, and that's the distance. It's basically gonna be the length of my pointing finger, so from my pointing finger to the knuckle of my thumb, and then the length of my thumb, right? That's gonna be my Manhattan distance from pointing finger to the thumb. But that may be kind of counterintuitive to, you might just say, well, why not just draw a line, right? We have kind of a triangle here. Give me that hypotenuse, right? And that's going to be our distance. That's shortest distance between the two. But you can see how when someone says, well, what's the distance? You may say, well, what do you mean? Right. If I say the distance from my pointing finger to my thumb, you may also say, well, what's the cosine distance? The cosine distance looks at the angle here, right? See, how many degrees is that angle? Oh, is it let's say 45? Right? If this is, you know, a right triangle, it's going to be 45. 45 divided by 360, that's the going to be actually the cosine similarity. 1 minus that is a cosine distance, right? So that gives us, I think I maybe flip that. So this is going to be the cosine distance that we get there, and then we subtract that from 1 to get the cosine similarity, right? So we've got, because the larger this angle, right, the more dissimilar. Okay, so this has to be the distance. At this angle, that's the distance. Okay, good. So pretty interesting, right? So let's maybe draw this really quick. So I was using my hands, and I don't know how useful that is. But let's draw this really quick. So I'm going to have, what's the distance between this line? Oh, between here, this point. I'm going to kind of draw this triangle that I was talking about. Okay. What's the distance between, let's do green. I'm already in Christmas mode. What's the distance between the green and blue points? Okay. So for Manhattan, we would go along here and then up here, and that's the distance. Okay. For Euclidean, we would draw a line like that, and that's the distance. For cosine, what we would do is we would look here and see, what's this angle? 45. Okay. So we've got, you know, in 360 degrees, we've got, you know, 45 degrees, it's going to be an eighth, right? So 1/8 is going to be the distance here, okay? And so it's bound between 0 and 1, actually, right? Okay, kind of. That's like an approximation of what's going on, right? So it depends on this angle, okay? You don't have to know cosine. Just wanted to kind of give you an example of something else, something that's completely different, okay? A different distance metric. The ones you should know are Euclidean distance and Manhattan distance. So why do I have Minkowski distance here? Right? So Minkowski distance actually is something that's pretty neat because it's an approximation. It's not an approximation. It's a term it's maybe like a superset of distance metrics that includes both Euclidean and Manhattan distance. Okay, so in this equation, we're going to have this thing here. It shows up twice. We're going to have P. Okay, if P is 1, basically, what that means is we're only left with this part of the equation, right? Then we've got Manhattan distance. If P is 2, meaning that we square this absolute value, and then we take the square root, right, of everything, right? Then we've got Euclidean distance. And if P is, really anywhere in between, then we have to use Minkowski distance to describe it. And it's going to be, some blending of Euclidean and Manhattan distance. And how you can imagine it is if we've got maybe something where we're doing something in between, right? Where, maybe we're moving like this, where there's some penalization for going across, something like that, and one quick thing to note is Euclidean is also called L2 distance. Manhattan is also called L1 distance. Manhattan is city block distance. Short, Manhattan and city block distance, it's the same thing. So L1, L2, and then Minkowski can actually give you a blending of L1 and L2. Okay. All right, so L1 is going to be kind of jagged. Euclidean is going to be a straight line. And then Minkowski can give you something that's kind of like a smooth meandering one. Okay. All right, so hopefully that makes sense. These are the two distance metrics you should know. And in Scikit-Learn, in dbScan, you see here, you can set it to be pretty much anything you want, but Euclidean is the default. All right, let's go back to k-means.
I have a question.
Yeah, please go ahead.
Could you go over one more time how the equation correlates to the L1 and L2, the Manhattan and the Euclidean?
Sure. Let's maybe do something cool, okay? So if I go here and then I look in, I think what I'm gonna want is to just go into this notebook. And then let's see, I've got here a slide that I'm skipping, okay, because these are all these different distance metrics and I don't want to show you so many, right? But Euclidean, Manhattan, Chebyshev, Minkowski. Wow, but this is actually good. I probably should have shown this slide. I skipped it for time, but you see how Euclidean distance, it's this line here, okay? All right, Manhattan distance, you can't go diagonally, you got to go perpendicular. So you got to go to the right and then up. Okay. Chebyshev, let's skip that for now. We see how Minkowski is, you can get kind of like a smooth line in between these two extremes. Okay. And you can modify P, that P value to move between the extremes, to get something in between the extremes. I also mentioned cosine similarity. That's this one. You see here how there's that angle, right? It's that angle that we're interested in. Okay. All right. Now let's go here. So I've got here Minkowski distance. All right. And I'm going to copy this down and I'm going to make some edits to the math and, you know, don't worry too much about these edits that I'm making. So here I'm going to change it and say Manhattan distance. Okay. All right. And actually I don't need the parens anymore, right? So there's parens. Let's see. Let's get rid of this. So I need some. I don't need, right. Good. Okay, so it looks good. I like it. Okay, so here's Manhattan distance. What happened here? Okay, so I'm raising it to the power of 1, which is the same as doing nothing. Okay, and then here I'm raising it to the power of 1 over 1, which is 1, which is again the same thing as doing nothing. So with my Manhattan distance, yeah, I'm just, you know, I just have this absolute value. Why do we have the absolute value? Is so that positive and negative differences don't cancel each other out. Okay. All right. So let's go ahead and copy this down again. Okay, I'm going to make some more edits. But again, you know, don't worry about this live coding that I'm doing. Okay. Now P, I'm going to replace P with 2. Okay. All right, and this is going to give me Euclidean distance. Okay. And so for Minkowski distance, P can be anything between 1 and 2. And we get that range of values. Okay. With Euclidean distance, what we're doing is we're taking these absolute values of these differences, right? So the positives and negatives don't cancel each other out. We've got the absolute value. We're summing up these basically distances squared. Okay. And then we take the square root. So raising to 1/2 power is the same as taking the square root. Okay. And so here, this is, you know, we're getting out, you know, getting these distances of individual points. We're squaring them, we get the sum of squares, and then we take the square root. Okay, so that's the Euclidean approach, right? And Manhattan is a blending of the two by setting P to be simple. Yeah, if we set P to be higher, right? So let's see, P is almost 2, right? We're going to get something that's pretty much a straight line. It's a little bit curved. If P is closer to 1, what we're going to do is we're going to get a curved line, but it's going to be kind of heavily curved. It's going to be close to what we would get with Manhattan distance. Okay. All right. Thanks for asking that question. It's a great question.
Yeah, thank you.
Yeah. And you'll see here, all of this, there's a lot there, more than what we need, okay? Both dbScan and k-means use Euclidean, okay? So if we look at k-means, so here what is going to be, okay, so k-means we have to look a little bit closer in the documentation. Where is it going to be? So for k-means, it also needs this. Does it not? Looks like it doesn't include it, right? But we also need to absolutely have distance there. Okay. And then you'll see how there's a little bit of you know, something similar here. Okay, so really what it's working with is inertia, right? So this is how inertia is calculated. This is basically sum of squared distances. We can call it also sum of squared errors. And this is going to be what we're trying to minimize, right? So, okay, so it doesn't use Euclidean, it uses inertia, of course. Okay. All right, and then yeah, inside this user guide, let me actually share this because it's pretty good. It's showing you what are the problems, or so here, here we have wrong number of clusters. So we needed 3, we have 2, and we got a result that's not great. Here, these ones are ones that are not really distributed the way we want, right? So this is anisotropically distributed, right? We want them to be really kind of like multivariate Gaussian, multivariate normally distributed, right? Here we've got unequal variance, so there's more spread for some of them than others, right? And then the sizes here are different. Okay, so these are all things that cause problems for k-means. Okay, good. Okay, so that's good. So we've talked a lot about distance, but distance certainly is important for all clustering algorithms. All right, now we're getting into some code. All right, so we have here some imports. And what you're going to need for this is you're going to need to have some kind of Python distribution with these things installed. If you don't have Python installed, you've got to install it. The one I think I recommended was Anaconda. If you've done some coding already, all right, so here let me share this link. All right, so this is what I recommend that you use. Do I use this? I don't. I use something that I manage on the command line. So Anaconda is going to give me a graphical package manager, and I use a command line package manager. If I say which Python, so mine, the distribution I use is called Mamba Forge. Okay. And it's something that you have to use the command line to manage. If you are not comfortable with the command line, you absolutely want to use Anaconda, right? And it gives you a graphical installer, it gives you a graphical user interface for managing installation. It comes with all the things you need. You don't have to use the command line to install. Okay, maybe it doesn't come with all the things you need. It'll come with all the things we need for this course, I think, and for today gives us everything we need for today for sure. Okay. All right, so I'm going to run these imports. Okay, so you see here it's running, there's a little asterisk, and then I've got execution count 1. This is the first cell that I executed. How did I do that? Well, I clicked on it and then I pressed Shift Enter to run it. You see now the execution count is 2. I've added on more than, okay. All right. Okay, so we're going to do a little bit of a plot here. So here we've got this, we've got a red dot and a green dot, and we can say, well, what's the distance between them? All right, I'm only going to focus on Euclidean and Manhattan distance, right? Okay, so first I plot these points. Okay, this is the code. You don't have to worry too much about exactly what the code does, but we're plotting these 2 points. The coordinates for one of the points, right? X is 1, Y is 5. For the other point, X is 2, and then Y is 4. Okay, so the Euclidean distance here, what it's going to be is it's going to be the hypotenuse. So here I'm going to do some annotation. Okay, between these 2, and then there's more than one way to draw it, right? So you can see how you can probably see we've got a square, and we can make 2 triangles from that square, right? So each square can give you 2 triangles, right? 2 right triangles. Okay, so here's one triangle, right? You can absolutely also do another triangle, right? Starting here, right? They're both going to have the same exact hypotenuse, right? What's the hypotenuse? I'm going to make that one orange so that it stands out. Hopefully it's visible, right? So here, that's the hypotenuse, okay? So we got our hypotenuse here. I can tell you that each of the sides of this square are 1. Okay, so it's from 4 to 5, and then from 1 to 2, right? And then this, what I'm expecting the length of this hypotenuse to be is I'm expecting it to be the square root of 2. Let me see. So here it's 1.4, and then I have NumPy. I'm going to have square root. I have the square root of 2. And you see how, so the sides, the smaller sides of this right triangle, it's a right triangle because I've got a 90 degree angle here. Opposite the 90-degree angle, I have my hypotenuse. The length of the hypotenuse is the square root of 2. And the other sides are each 1 in this situation. Okay, good. All right, so let me clear this drawing, and then we'll move on. Okay, so for Euclidean distance, it was that hypotenuse. All right, now what about Manhattan distance? Okay, Manhattan distance, the Manhattan distance is 2. Okay, why is that? Well, because I can't go diagonal. I got to go, let's say, here from 5 to 4, that distance is 1. And then here on the x-axis from 1 to 2, that distance is 1. So it's 1 plus 1 is 2. Okay. And if I was using Minkowski distance and modifying P, okay, in this example, the closer that P is to 2, the closer I am to this being the distance. And then the closer that P is to 1, the closer I am to the distance between these 2 points being 2. Hopefully that makes sense. Okay. All right. So here you can see a lot of different distance metrics. So Euclidean, Manhattan, cosine. There's also correlation. Okay. Cosine is out of scope. Correlation is out of scope. Correlation is definitely a very, very, very important concept. But we'll move on from that for now. For binary data, you can also use these other distance metrics, Jacquard and Hamming. I think this is a super good example, but let's skip that for now, okay? Because I want to get to actually doing some clustering, right? So we've got here some synthetic data. We have from Scikit-Learn imported make blobs. We run make blobs, and we get out some blobs or some clusters, okay? And then we're going to, so we're able to create a data set, a synthetic data set. So how many rows are we going to have? So rows are samples, okay? We have 30 rows, okay? We have 4 clusters, so cluster centers are clusters, okay? How many columns do we have? Columns are features. We have 10 columns. Random state is 0. This makes it reproducible. Any integer you put there is fine. 0 is a great example. And then what's the spread of the clusters? How dispersed are we going to have? Standard deviation is 1. So these blobs, have unit variance, have variance of 1 standard deviation. Okay. All right. Good. So then we use heat map, and we can see this our data set in a heat map, right? So what's something I can add to this heat map? I can say Anna equals true, and I'll get the actual values. Is that going to be good? Right? Is that going to be helpful? No, maybe not. I don't think so. It kind of makes it a lot harder to read. If I made this much larger, so let me see. Okay, so do I have PLT? Yes. If I say PLT figure, and then inside of figure, I have fig size. And fig size, I'm gonna say 9 by 9. Okay. Let me put this here. Okay, so that's better, right? You know, and is this color bar really helping? Maybe it is, maybe. What's also something I would do here, right? I would want to make it, if the color bar isn't helping, I can do C bar equals none. Okay, so let's do C bar equals false. False, I could also, I see I was instinctively doing. Let's try none. Okay. And then square is the next one I want to do. So let's make it square. I think that's going to make it easier. Okay. All right, but clearly I've hit a bit of a problem here. Where I think it's no longer increase the fig size. Okay, that's better. I think I was just having trouble with the size. So it's actually not square, and I'm kind of unsure of why that is. Maybe it's that fig size. The fig size was good. Maybe having it be square was not as helpful as I thought. Okay. I think yeah, I think this is probably good. I'm having a little bit of trouble controlling it, to be honest. Yeah, but you can see these are our data. Maybe I made it a little too big. Let's do 12 by 12. Okay, and this is probably optimal. If I zoom out a little bit, let's do. Okay, this. Let's maybe flip it. Okay. Yeah, if I zoom out a little bit, I think this is probably going to be correct. Okay, so you can see here I've got the values. The values work pretty well, right? What do I see in my values? I see that they range between, let's see, something like -10, and well, they actually go above 10. So here's an 11, right? Let's say from about 10 to about -10. That's the range. Okay. And it's kind of tough for me to see much of a pattern here looking at this heat map, right? I can see the fifth one, the one indexed by 4, has low values just in general. That's kind of what jumps out, right? Similarly, maybe this one, the eighth one, the one indexed by 7, has relatively high values to it. Okay, so those are things I can pick, right? Okay, then we can look here at a histogram of the distances, right? So it seems like there are some distances that are fairly large, and then other distances that are small. But in general, we've got distances, you know, that are fairly large, right? So here, the distances, so these are the actual values, and here are the distances. But typically, we've got, you know, we've got more large values than small. So that's what I'm seeing. Okay. There's also cluster map, which is, wow, look at that. That's really brilliant. We've got a dendrogram of the features, so tree plot of the features, and the dendrogram of the observations. So we can see how the features are related together and how the observations are related together, right? Okay, good. And then here we've got, this is again from Scikit-Learn, how different clustering algorithms behave on different data sets. We've got a type of k-means, of mini batch k-means, and dbScan. Okay, so for concentric circles, that's what I mentioned here. K-means really can't do it. Okay, it just draws a line down the middle and says, all right, those are the clusters. And I say, okay, maybe that's what we wanted, but that doesn't look that great, right? DB scan says concentric circles, no problem. Okay, I got this. Inner one is orange, outer one is blue, no problem. Okay, same thing with these. Let's say maybe this is kind of intersection and union symbols, right? K-means says, okay, I'm gonna just draw a line across two clusters. That's the best I can do. Okay, DB scan looks at this and says, no problem. You've got intersection, you've got union, no worries, two clusters, no problems. Yeah. Good. Then there are these other examples, right? So here we've got different variants. All right, and K-means struggles a little bit, but gives us something that's more or less sensible, more or less, right? DB scan says, okay, great, I can do this. But I'm going to combine these two clusters up here, depending on the settings, right? And then some of these random points out here, I'm not going to bother with. I'm going to have those be outliers. Okay. Okay. So you can see this is a good comparison of how these different things behave. Okay. You'll have different families of clustering algorithms. Connectivity, centroids, density, distributions, affinity. Do we want to discuss these? Maybe, maybe next class, but then some of these, would be like next classes. If we had more time, we're not going to get to them. We want to focus on K-means and then DB scan. Okay. So here we've got our K-means, we've got our centroids. Okay. Right now the centroids aren't in a perfect position, right? But we can see we can improve by moving them closer to the points, right? We're gonna be able to, get them to actually be in the center of the cluster. But already from here, you can see this is something that K-means is gonna have no problems with. We've got cluster 1, 2, and 3, blue, red, and green. And we've got K-means is going to be able to handle this notebook. Right? I also have in here, in this notebook, this is from a great guy named Chris Alban. He has these machine learning flashcards that he hand draws himself, hand writes himself. And I have this one. He gave me a free copy of them at one point. I forget why. I think I volunteered to read an updated version of his book. He had way more readers than he needed. And he said, okay, as a thank you for just volunteering, here's a free copy of my machine learning flashcards. Wow, that's so kind of you. I did absolutely no work, and you're still giving me something in return. Okay. All right, and so I included that one here. It's Chris Alban. You can find him on Twitter. He also has a great blog. Okay, and then you can see here the two cluster centers, and they're moving towards the cluster centers. Really, I mean, like towards the central point of the cluster. So the centroids are being adjusted, and then the cluster assignments are adjusting as the centroids are moving. Okay. So basically the steps in the process, you have your centroids, you assign clusters, and then you just repeat those steps until you converge, or you've hit the max number of iterations. Maybe you want to say, all right, just go through 10 iterations, don't work after that. Whatever answer you have at that point, that's it, we're done. Okay. Okay, so here it is. It's working based off of inertia, which is sum of square distances. Okay, within a cluster. Okay, and then the lower the inertia, the better. Okay. Oh, and then here I've got mean shift. Do we want to talk about mean shift? Let's maybe skip mean shift. We've got density-based spatial clustering, or DB scan. Yeah. So here, what is it doing? It's looking in the radius of points and seeing, okay, in the radius of these points, do we have enough points to create a cluster? Right? Can we hit our min points? And see here, this is our this is a GIF of exactly what we were looking at, right? The smiley face. All right, so here's the machine learning flashcard for DB scan, right? In terms of how it works. Okay, if something isn't assigned to a cluster, then it's marked as an outlier. Okay. Then we've got hierarchical clustering, and I think hierarchical clustering it's useful to talk about. Okay. Why is hierarchical clustering useful? Hierarchical clustering is useful because you can get this tree plot, this dendrogram from it. It also uses Euclidean distance, or let's say it also can use Euclidean distance. You can use some other distance metric, right? This tree plot, this dendrogram, is very useful for understanding our clusters. Where did we see something like this before? We saw something like this in that cluster map, the heat map with the dendrogram on each side. We can cluster the features, yes, but this would be a clustering of the observations. So it would be the one on the side, the one on the left side of that heat map. Okay, I'm going to go back to that. So I had a colleague who would always say, before she would scroll through a Jupyter notebook a lot, she would say, hold on to your eyeballs, okay, because it can be a little bit disconcerting to see me scroll like this. Okay. So wait, I'm past it. I went too far. So that's the heat map. This is the dendrogram here, and this one goes to completion. Works until purity, until we have actually what it does is actually not just the purity, it goes into completion, it basically grows the tree completely. It goes all the way until each leaf in the tree, these terminal nodes are called leaves, has a single observation. We go down to each row. Okay, but we could slice this. How do I say no? My phone is ringing. Okay, I'll have to check what that is later. I just got a new phone. I should set it to silent actually. Okay, I got the newest iPhone and I actually got the newest, coolest iWatch, Apple Watch. And my fiance makes fun of me because I don't know how to use either. I'm like a tech expert, and I'm like asking her all the time. How do I do simple things? And then I even feel strange wearing it because I have no idea. I have no idea. It like vibrates. I'm like, why is it vibrating? I have no idea. It beeps. I'm like, what does that mean? You know, and I have no idea how to use it. Okay. But anyway, so what we can do is we can slice basically. It's simple, right? So here I'm going to pick blue, I think is a good color. And I can slice here and I can say, okay, listen, having a single cluster, having one observation, having each observation have its own cluster is useless, is meaningless. I want to learn about groups of observations. I don't want each observation to have its own cluster. I learn nothing. I'm going to slice here and I'm going to say, okay, instead of growing the tree from the root down all the way to every single observation, I'm going to have 4 clusters. Okay. What are the patterns in these clusters? Okay. So let's look at the bottom cluster. Okay. So the bottom cluster, I'm just going to use kind of colors to describe this, right? It's going to be kind of orange, red, then I see a block of maybe orange, then red, then orange, and then a block of dark. Okay, so that's the pattern. In this cluster here, one of 4 that I've chosen, I've chosen to have 4 here. Okay, I see this pattern. It's like a barcode, and the observations, they follow this pattern. They have that in similarity, right? So for features, the features indexed by 4, 5, and 7, so the 5th, 6th, and 7th features, right? They're all low in that feature. Okay, they have that in common. They have fairly high values for all the other features. Okay, that's what this cluster has in common. Okay. Let's look at the next cluster up, this one here. What do they have in common? Well, they're very low in features 4 and 6, but not 5, not the others. Okay, so the 5th one and the 7th one, but not the 6th. Okay, and then we're starting at 0. So feature 4 is the 5th one. Okay, hope that isn't too counterintuitive. Okay, I could also do something else. I could say, listen, 4 clusters, too complicated. I only want 2 clusters. I'm going to slice here. Okay, so I'm going to get the bottom 2 of the original 4 and the top 2 of the original 4 that I was talking about earlier, right? Okay, so what do they have in common? All right, so I would say is that in general, they're low for 4 and 6, okay? Whereas that's not what we see up here, okay? This of the 4 original clusters, the top one is low for 4, but not 6, okay? So that's the pattern that I see, okay? If I were really looking at these data and I would say, what do I want? I would probably want 4 clusters because I can see the patterns there. Okay, and I'm purposefully scrolled down past the dendrogram for the features. You can absolutely also look at that. Okay, I bet that heat map has some parameters for this, right? That I can change this. See, row cluster true, call cluster also true. Let's turn it off, right? Instead of just me scrolling down, let's put false. Okay, you see? There we go, because I wanted to focus on this. Because in clustering, we're putting together rows. If we were putting together dimensions, putting together columns, then that would be a form of dimensionality reduction, right? So we could somehow combine the values. Maybe we cluster and then we take the averages, right? Maybe that's what we do, right? But if we were working with columns, then that would be a dimensionality reduction technique. We're working with rows, so that's a clustering technique. So this here, what I have there, that is literally clustering. This is clustering. This is hierarchical clustering, what we see here. Okay. All right, and it's picking up on patterns in the data. Okay. This one, I think that's it. And it looks good. I think this looks pretty good. Maybe this color bar isn't that helpful. So if I do C bar equals none, none is shorter than false. Oh no, I think I want it to be false. Why is it still showing up? Okay, so that's so interesting. Maybe I just shouldn't touch it. Okay, just leave it. All right. Okay. So I have here my cluster. And I can do that same thing with an algorithm without that heat map, right? Here, okay? So how does it work? At least agglomerative clustering, how it works is it's going to start with all of the observations individually, okay, in their own clusters. That's not useful. Doesn't teach me. I can't learn it. So what it's going to do is it's going to find the observations, the two observations that are closest to each other, the ones that have the smallest distance between them, and put that first into a single cluster. Okay, that's going to be this first cluster here. Okay, that's the first cluster. Then it's going to say, okay, now that I've made that first cluster, what are the smallest distances after that? That's going to be this cluster here, right? After that, what does it do? All right, so let's see. So we put together these two, then we put together these two, and then we put together here, this green one. That's the next step. And then the step after that is this. Then the step after that is we put these together. And then finally, we put all of the observations together. And when we get to that, all the observations are together in the same cluster. That's the root node. That's the root of this tree that we've created. Okay. All right. So this is good. We can use this clustering diagram, this dendrogram, to understand our clusters. Okay. To understand our data. Right? It's useful. And with the heat map, actually, I think it's even more useful, right? And we can use that to try to understand what our clusters are, right? Okay, good. So let's move on. Okay, so that's agglomerative clustering. All observations start in their own cluster, and then they're merged together, going from the shortest distances to eventually everything is merged together. Process is repeated, clusters grow until some endpoint is reached. You know, really the logical endpoint is that everything is in one cluster, right? Okay, so here we've got the iris dataset. This is the dataset we're going to be working with. And this is the nicest picture I could find that describes the parts of this iris flower that we're going to be looking at, right? So it has a unique anatomy, right? So it's got petals and sepals. Okay. I'm actually not sure how to pronounce this word. I don't think I've ever heard anyone say it out loud. Maybe they're sepals. Probably petal, sepal. That makes sense to me, right? If you know how to pronounce this word, definitely let me know. Okay, let's say petals and sepals, right? So we've got these are these parts of this flower. So what we're going to try to do is we're going to try to classify these flowers into different species, and we've got 3 different species based off of measurements of the petals and sepals. Okay. So what are the measurements? We're going to measure, we have the length and the width of the sepals and the petals, and then we've got the species. All right. So in module 1, you did some pandas work, right? Let's go ahead and look at the data set, right? So we're going to have iris. Okay, so we loaded that in. Where did we load it in from? Well, we loaded it in from Scikit-Learn datasets, and there's a function load iris, right? So what is this iris thing? Okay, if I let's maybe so here to put in a split. Okay, what I do is I have a keyboard shortcut Control-Shift-, and then to put in a cell above, I press A. So I click on a cell like this, not in a cell, but next to it, and then press A to create a cell above. All right, so we got this iris thing, and I want to show you what is it first. Okay. So I rerun this code. I look at iris. Iris is gonna be this. It's a scikit-learn. I think it's called a bunch object, and it's gonna have data there. It's gonna have different things. Okay. So how do I know what's in there? I've got a quick way of doing it. I press after I type iris, I press dot, and then I press tab, and I see there are these different things. Okay. So there's the data. There's a description of the data. There's the names of the features, file name, frame, target names. Okay. So I'm first going to look at the description of the data. And this I know already from prior experience with this, is that it helps if I print it. Okay. Because otherwise it's just going to be tough to read. Okay. So it's a data set looking at iris plants. Specifically, we're focused on the flowers. We have 150 instances. Instances is another name for a row. So observations, samples, examples, instances. I think I said instances, yeah. When I was talking about all these different names for the rows, right? These are our data points, okay? And we have 50 of each class. What are the classes? Classes are iris setosa, iris versicolor, and iris virginica, okay? We have 4 attributes. These are our columns. The 4 attributes are sepal length and width, and then petal length and width. I don't know why. Is it sepal? Is it sepal? I don't know. Measured in centimeters. Okay. And then some summary stats. Yeah. Okay. And then a couple interesting things here. So that's the description. I can also look at the target names. Target names here, setosa, versicolor, and virginica. Good. I can also look at the feature names. Sepal length, sepal width, petal length, petal width. Okay. So inside of this scikit-learn bunch object, I've got all the things I need. I've got the data. I've got the labels, which is called target, the names of the features, and then the names of the targets. Good. Great. All right. So now what are we doing here? We're dropping some of the dimensions, right? So here we're going to do iris 4D has all of the 4 dimensions. So sepal color, sepal width and length, and then petal length, width and length, so the 4. And then we've got this other thing called iris. Maybe let's call that iris 2D, just to make it clear. Okay. So iris 2D is only going to have petal width and petal length, and that's it. We're going to fit now our k-means model to the data. So what does fitting the model to the data mean? That means that we're it's learning from the data. Okay. All right. When we are fitting a model with Scikit-Learn, there's a standard workflow that we do. Okay. So up here, this is called importing. And we import the data. Then, sorry, not the data, the model. Then we're going to do instantiation. So we're going to instantiate. We import, we instantiate, and then we fit. Okay. All right. Good. Good. So we import, instantiate, and fit. Here we're doing actually fitting and predicting at the same time, which is great. Okay. So we import from the Scikit-Learn library. we're going into its cluster module. From the cluster module of the Scikit-Learn library, we're importing this k-means class. We're instantiating the class as models. So models are class instance. And then the model instance has this instance method that we're using to fit to the data and generate our predictions. Our predictions are our cluster labels. Okay. Great question, Francis. In unsupervised learning in general, you don't have data splitting. No training set, no validation set, no test set. You can, of course, do that, but you don't have to, right? It's as if that concept doesn't apply. It's absolutely essential in supervised learning, but doesn't really apply to unsupervised. It's a great question. Okay, some of these are defaults, right? So this k-means plus, it's going to look at summary stats basically and decide what's a logical place for the cluster centers to be. We have 2 cluster centers. I know that's not going to be optimal because we created this data, it's synthetic data, and we need to tune this, right? We need to get to the point where we've got the right number of clusters, and we can try a different cluster, different numbers of clusters, and see which one works best for us in this current situation. Okay. Some of these are defaults. Okay. And if it's a default, then my recommendation is don't include it. These are included, so we can talk about it. Right. This is how do we determine where the cluster centers start? Then we say, how many different configurations of cluster starts are we going to try? Okay. Here we try 10. That's the default. That's fine. So I'm deleting these because they're the default. We don't have to set them. How many iterations do we want to go? 300. And then here, what's the tolerance? Okay, so don't worry about that. That's the default. So basically, what are we setting here that matters? Number of clusters, and then the random state. So the random state is 1, 2, 3, 1, 2, 4. It can be any integer. This is just for reproducibility. If we set the same number here, we're going to have the same result. Okay, that's what we're trying to guarantee. Really, for it to be guaranteed, we'd have to be running the same version of the software, on the same data, in the same operating system, the same computational environment. Okay. Okay, so that's really what's required for reproducibility. But this should work. Okay, should be enough to get us there.
Professor?
Yep.
I'm getting an error message when I'm trying to do this as well. It's saying the float argument must be a string or number, not bunch.
Good. Okay, so here, I'll do an explanation, and then I'm going to ask you to share your screen in just a second. So what is bunch? Okay, so if we look at type of this iris thing, right after I loaded it in using this function, see, it's a bunch object. What is a bunch object? A bunch object is like a dictionary, right? Where I'm going to have these different things, right? It's like a Python dictionary, right? So here I've got data, and the data is this array. And I'm going to have other keys in there, right? So I can access those keys like I would in a Python dictionary, right? The easiest way to troubleshoot what you're looking at is for you to share your screen, and I will, I think maybe what's happening is that we need to pass in something that just has the data and the target, without any of these other, you know, it can't be this bunch object. It has to be one of these things, like one of these data frames.
Okay.
So maybe we can try it if you don't pass in, right? So here I changed this to iris 2D. Okay. And so what we're gonna need is when we get here to fitting the data, we pass in iris. Okay, we're gonna have to do pass in iris 4D or iris 2D, the way that I have it. Okay. Give that a try. It worked for me, but I think it's because I didn't run it.
Okay, yeah, the iris 4D worked.
Okay, good. That's all we need. Okay, so I think we're all set.
Great, thank you.
And then thanks for chiming in the chat. And then I don't know if that's your full name there, but I think it's Emil. I don't know. But thank you. Okay, and then it's either Emmanuel, as in like you know, with an American accent, or maybe Emmanuel, like that. Right, maybe Emmanuel. But thank you so much. All right, good. Okay. Good. Then we've got this function here for plotting k-means. Okay, so we define our function. We don't get any output from the function definition. But then what we do is we get an error. What did I do? Okay, it's because again here I have to put 4D. So I think this is the error. Yeah, so it says here, float argument must be a string or a number, not bunch. All right, so see, there I got it. I broke my own code. Here we did 4D. It's because I changed that one. Oh, what happened? Because I put it in two places. Here we go. Model predict, model fit. Because we separated this out into two. Why did we do that? Okay, now key error. Hello. So something here. I think it's yeah, the original data that I'm passing in, is it not a pandas data frame? It's a NumPy array. No, it is, but it should have ilog. That's very strange. That's an error that I don't really understand. Because this original data that I'm passing in, it's a data frame. It should have ilog for sure. So maybe let's just try iris 2D here. And see again what is going on. So iris 2D. Oh, here you see this. I need to change it here too. See, I make one small change and everything goes out the window, right? Yeah. So here I just need to change it in both. It definitely wasn't worth it to change, right? But this is iris 2D. I did want to change the name because it's two-dimensional, right? 2D, right? And then what are the two dimensions? Let's look at iris 2D, sepal length and sepal width. Okay. And here what I would have wanted is maybe for this plot k-means to also give us the labels, you know. So of these, right? Which one is width, which one is length for the sepals, right? I don't know, but it gives us a nice plot. So you can see the red dots are the cluster centers, and then you can see the points that belong to those clusters, right? So cluster 0 is blue, and it has this center on the left, and the center on the right has orange. Okay, so that's really great. This looks really good. Very nice plot. All right, if I do say so myself. And then, you know, is this what we want, right? Here, if we had 2 species, this is probably going to be great, but 2 is not enough for this data set because we've got 3 species, right? And then before, when I said I did say 2 is not enough, there are 3 species. I was also thinking that blobs data set, if we wanted to cluster that, there we had 4 centers, right? So we would need to have k-means with 4 clusters. Okay. All right, good. So I'm very happy with this. Here, this is with 4D, right? But we're still plotting on 2 dimensions. Okay. We see we get a slightly different result. Yeah. Then we use the 4D data with 3 clusters. And one thing that is good to note is that when we're using more, we're doing more data, we have more dimensions than what we're showing. We're only showing 2 dimensions, right? Okay. It's not going to look absolutely intuitive to us, right? So you see here how there seems to be kind of like a blending between cluster 2 and cluster 1. Cluster 0 looks fine, right? But here there's some blending. You say, well, that's weird. It doesn't look like they're really, it's not picking the points closest to the center, right? Why are there some orange ones here mixed in with the green? It's because they're dimensions we don't see on the plot. Okay. We can only show 2 dimensions on this type of a plot unless we do dimensionality reduction. Okay, and then we can show basically some things. We're still showing 2 dimensions, but those 2 dimensions are going to approximate more dimensions. Okay. Are there small clusters too? Maybe, you know, here in this example, I know there are 3 species. Okay. But maybe we could look here and say, okay, maybe we want more than 3 clusters. Maybe there are subspecies of flowers, right? Maybe, you know, we would have iris versicolor grandiosa. I don't know. I don't read that. It's not a real thing, but you know, like a subspecies, something. Yeah. So it could be that there are smaller clusters. Okay. So evaluation of clustering. Okay. So this is where you know, we can do some really cool stuff. We can talk about the elbow method. We can talk about silhouette coefficient. We're not going to have time for that today. Okay, that's going to be for tomorrow. All right. What I'd want to do, because I think it's like a perfect example of exactly what I said, is we're going to do from scratch. We're going to do PCA. Okay. And I'm going to live code this, and you're going to see me live coding. And I think this is very useful. I like live coding. I enjoy doing it. I think it's a great didactic tool. So it's great for teaching. And you can actually see, you know, how the code comes to be. You can see my process. Because if you're just running code that already exists and not writing it yourself, you're missing out on that part of the process. Okay. So what do I want to do? I want to take my 4D data and I want to do dimensionality reduction on it. And I'm going to take, you know, the I'm gonna specify that I want to take those 4 dimensions and turn it into 2. So I want 2 principal components. I'm gonna go from 4 columns to 2 columns. Okay. There's probably a logical way that I can describe those principal components, right? I would expect sepal length and sepal width to go together, right? Either you have large sepals or you have small sepals, right? Same thing with petals. Either you have large petals or you have small petals. So I would expect the width and the length to kind of go together, right? And then very literally here, actually, what I'm going to do is I'm going to go back to that diagram of the flower because I think that's going to be perfect. Okay. And I'm going to draw some lines here. We're talking about dimensionality reduction now. Oh, wow, right? What about that for a second? Okay, so here's a petal. And I'm going to use this petal. And so we're going to have the length of the petal is like this. And we're going to have the width of the petal. Okay. I expect these two to be correlated. Okay, of course, you can have a different shape. You can have it be longer and thinner, right? Not as wide. That can happen. But I would expect these two to be correlated. Maybe they're correlated, right? If they're linearly, if there's a linear relationship between the two, they're correlated. And then this is perfect for dimensionality reduction. Instead of having 2 things, I can have just 1 thing. I just have the size, which is a combination of the width and the length. Okay. So I'm going to go and then just say, all right, so width and length both contribute to the size. When width and length are small, that's a small size. When width and length are large, that's a large size, right? And this is how I do it. Okay. So how does this work in theory, right? So I'm going to have my 2 axes, right? So this is going to be, let's say, length. Maybe that's width. Maybe this is length. It doesn't actually matter. All right. And so I've got my 2 dimensions. And I'm going to have some data points. And I'm expecting those data points to be correlated. So here's a data point, right? So there I've got a width and a length. Here I've got a width and a length. Here I have a width and a length. Here I have another width and a length, and I'm going to do just 1 more. Well, maybe let's do 2 more. Okay. All right. So here I've got my data, right? And I see that there's some linear relationship here between width and length. All right. Between these data sets. So what am I going to do? Well, the first thing I instinctively want to do is I want to draw a line. All right. So I've got this line, right, between width and length. All right. And this line here actually is my what I would call a principal component, my first principal component that summarizes both width and length. It includes both. I can take this line and basically rotate it, right? Like this, okay? And then this is going to be size. And then I know there are points that don't fall in the line. That's okay. I can basically say, all right, I'm just going to do the best I can. If it's not on the line, I'll just draw a line like this and say, okay, that's where it would be on the line. Okay, I'm going to draw these kinds of perpendicular lines, right? Okay. Wow, I'm really bad at drawing these perpendicular lines, but I hope you know what I mean. Okay, so from the line going straight up or down to the data point. Okay, and that's where it falls on the line. Okay, so now I have a single dimension, right? And my data points, they all fall on this line. So if I was going to recreate this, I would basically say, just, kind of imagine here's a point. I'm really bad at drawing. And then I've got kind of like 3 points here, close together. Oh, why is it? Why is this so hard? Okay, here's a point, here's a point, and here's a point, approximately. Okay, and then I've got all my points on a line on a single dimension, and this is size. I call this size. It's the size of the petal. And I do the same exact thing for the sepal. Okay, I've got length and I've got width, and I combine those together, and that's my dimensionality reduction. So imagine that, I don't actually see the whole sepal here, but I would imagine, say it kind of ends here, and then my width maybe is going to be like that. Okay. And imagine that that's perpendicular, those are perpendicular lines. Okay. But here I have my data points here on a single dimension. And this I would just summarize as petal size. I can do the same thing. I'll have sepal size. And I went from two-dimensional space to a single dimension. Okay. All right. So here, let's just look here. So this one here that's furthest to the right has the largest petal. This one here that's furthest to the left has the smallest petal. And then I've got my data points in between. Okay. But this is what principal component analysis does, which is a dimensionality reduction technique that we're going to do now. Okay. So that's what it's doing. And I'm going to get two principal components, basically these orange lines, right? One for petal, one for sepal. The principal component for petal is going to have width and length combined together for petals. And then the principal component for sepals, it's going to have the sepal length and width combined together. Okay. All right. So hopefully that makes sense. I think this is a really good example of something you would combine together. Okay. What's another example of something you could combine together? Let's say something that yeah, so size is a good one. Let's say we have objects, and those objects are they all have the same density. Okay. And then I have a bunch of attributes of those objects. They all have the same densities is a key thing. So density is mass over volume. Okay. So for those objects, I've got height, length, width, mass, and then weight. Let's say, no, that doesn't make sense. So let's just say height, length, width, and then mass and weight, they're the same. Okay. But if they're all the same density, then those things all move, as the size increases in height, width, length, so will the mass. Okay. So we can combine height, width, and length to be volume. Okay. And then if it's the same density, if the volume increases, the mass has to increase because they're all the same density. Okay. So I could combine actually height, width, and length and mass into a single measure, which just would be size. How big is this thing, that has all the same, they all have the same density. That's another example, a very similar example, okay, of dimensionality reduction. Okay, we don't have too much time left. I want to do some live coding, and we'll pick up with this next time when we start again tomorrow. But I'm gonna do some live coding. So from Scikit-Learn, the decomposition module, import PCA. Okay. There's a question. If possible, can you please also do a case study of time series data for seasonality cluster trends, as in air quality data sets? So I think that's a little bit out of scope for this course. Time series analysis would be something different. You can do, I could absolutely do it. I've taught courses on that before. It's out of scope. we could do clustering on time series data, but it's a little bit of a different situation, because for time series data, our rows are time steps. And would you cluster the time steps? Yes, absolutely, you could. Does it make sense to? I don't know. I don't think so. The time steps are already, they're continuous, they go in time. You could cluster them and say, okay, well, listen, these ones from last month are most similar, closest to ones from this time of month, but there are other time series analysis techniques that I think we would do before them. Yeah. Can I give references? References for time series analysis? I don't know. And then clustering in time series analysis, I also don't know. Let me get back to you on that. Time series analysis is a huge, broad, big thing. And I would have it be, another module in this. Let's maybe have that a discussion that we can have later on. If there's yeah, maybe we can plan that for another module at some point, which would be time series analysis, and we can do an air quality data set for sure. But that's something, again, I would have a completely separate module for it. Okay. Okay. All right. So let's jump back to this live coding that I'm doing. So I import PCA, and I have PCA. So PCA is principal component analysis. And I have here this PCA class. Number of components is none, but I want 2 components. Okay. So I'm going to do n components equals 2. And I'm going to instantiate this. And I'm going to go from uppercase to lowercase. I'm going to say PCA. All right. So I instantiate it. And I'm going to do now PCA and look for a method. I want to fit and transform. I'm going to do 2 things at once. I'm going to drop in my data. So my data there is going to be iris 4D. Okay. And I'm going to say, let's call it iris. I already did iris 2D. Let's do maybe like iris PCA. Right, it's maybe iris 2PC. Does that make sense? 2 principal components. Let's do that. Naming things is hard, right? There's a saying in programming, computer programming, there are 2 things that are difficult, right? Cache invalidation and naming things. That's the real saying, but the joke saying is in programming there are 2 things that are difficult: off by 1 errors and that's it. And if you're not laughing, it's because it's a joke about programming. But the joke, to explain the joke, is I say there are 2 things, but I only provide 1 because it's an off by 1 error, right? Okay. So what's an example of an off by 1 error? It would be something like this, where I say I've got a list. The list has 1 thing. And then for the 1 thing, I say, okay, give me the one indexed by 1. But there's no such thing there. I needed to do the one indexed by 0. I was off by 1. That's an off by 1. Okay. What's a better example of that? I say, okay, I'm going to use the length to find out what the last item is. And I say, nope. All right. I was off by 1. Okay. All right. So that's an example. All right, so I've got my transformed data. All right. Now I can look at this data, 2PC. What does it look like? Oh, wow, look at that. That is so interesting. I have just 2 columns. The shape of my data went from 4 columns to 2 columns. I still have 150 observations. All right. So now what am I going to do? I'm going to use this the same approach. Okay. But I'm going to use this data set. I'm going to do PCA and then clustering. Look at that. Dimensionality reduction and then clustering in the same coding example, right? That's pretty brilliant. So I instantiate k-means as I did before. I don't need these defaults. Okay. Okay, and then I'm going to fit it not to Iris 4D. I'm going to fit it to 2PC, 2 principal components. Okay. And I'm gonna maybe let's fit predict. How about that? That's gonna be easier. Right? I have to do 2PC here, and I have to do 2PC here. Okay. Good. Good. Everything looks good. All right, so let's try it. Oh my goodness, what does it do? Okay, so NumPy array has no attribute iLock, and I know exactly what I need to do there. So this 2PC, what I really should have done with it is I should have turned it into a data frame immediately. Okay, so I saw the error of my ways. Okay, there's my data frame. Okay, and I'm going to continue on. All right, good. Wow, amazing. Amazing result. I'm fitting on 2 principal components which contain information from 4 features. And I look at my plot and I say, now everything makes sense. I can see how all of these green observations are together and all these orange observations are together. Okay, I can look at it in 2 dimensions. And actually, I'm getting better separation, at least between cluster 0 and these others, right? The separation between cluster 1 and 2, it is what it is. You know, it's not a trivial problem, right? There's some, let's say there's a gray area there. Okay. In terms of what is which species. Okay. All right. But these results look really good to me. Okay. I'm going to share this. Okay. In the chat, because this is not included in the original notebook. But it looks really good. And I hope it'll work for you. I think it should. And it's, in just a handful of lines of code, we can get to this nice plot. Okay. And this is a PCA plot. Principal component 1 and principal component 2 are the axes. Okay. Good. Copy and pasting is not enabled in this meeting. Well, there's not a thing that I can do to fix that. There's one more thing that I wanted to do, okay, which is to show you how we can kind of simplify this code. All right. So I'm going to copy and paste, and I'm going to say from sklearn.pipeline import pipeline. Okay, and then I'm going to create a pipeline. So my PL, let's say it's maybe pipeline. Okay, and my pipeline is going to have a list of things. My list of things is going to have PCA, and that's going to be here, PCA with 2 components. Okay, that's one thing. What am I doing? It shouldn't be a dictionary, it should be a tuple. And then I'm gonna have my k-means, which is gonna be my k-means with cluster 3. Okay. And then I can close out my list, close out my square brackets. And I think that's going to be it in terms of my pipeline. Let's put a little line break, a little break here. Well, you know, let's bring it back because let's do. Let's put a line break here, and then just see, does this work? It works great. Okay, I've got my pipeline there. Excellent. So what do? I set up the data as the same exact way. But I'm gonna do now PL is gonna be my model, right? Does PL have fit predict? It does indeed. Let's see if this is gonna work, okay? Because there's a difference here between fit transform and fit predict, okay? And then let's see if I can combine these two steps together. All right, so I would need to do iris 4D here. Gives me the cluster labels. Oh, you know what? So here, this pipeline thing, it's not going to help me too much because I do need these two things separately. I would need fit transform separate, and I would need fit predict separate because I'm using both, right? All right, let's maybe let's just do fit predict, which works beautifully. Do I get out my cluster labels? I do, and it looks beautiful. Okay, so let me share this code. So for plotting, it didn't really exactly work because, or at least it's not like super great. I would have to do fit transform, right? And it's just not. Let's just call this iris PC. Okay, so I'd have to do something like that, right? But if I was going straight to the cluster labels, this pipeline would be helpful, would be useful, because I can combine these two steps. First the PCA, then the k-means together into one step. I just do fit predict, right? And I get out my cluster labels, right? Are the cluster labels the same? I think so. I think they more or less work the same, right? Good. So let me, so I'm gonna copy and paste this code in there just because, you know, so you can see it. But then I'm gonna share the notebook.
I have a question again, Professor.
Yep.
I'm getting the error that like my k-means, my capital K-means is not defined, even though I think we defined it.
You gotta import it. That's the part that I skipped because it's at the top of the notebook.
Gotcha.
So Scikit-Learn cluster import k-means. Yep. And that's how I should have shared it. Let me make these things kind of, you know, standalone. Okay.
Oh, okay.
So I'm gonna save the notebook. I'm gonna share the notebook. Okay. We are out of time. I don't want to keep you over. We're exactly at time. I'm gonna share this notebook. And happy to stay on and actually answer questions. Okay, so shared the notebook, sent successfully, should be able to download it. If you need to run it, grab it, download it. I'll see you tomorrow, same time. If you have questions, happy to stick around and answer those questions.
Thank you.
Yeah, thanks so much. It sounds like there are no questions, and that's fine. We answered a lot of questions throughout. Let's go ahead and call it a day. And I'll see everyone tomorrow for the next part of this module.
All right, thank you, Martin, and thank you all for coming. As Martin said, we'll meet again tomorrow. Again, please take a moment. There is a survey